The Cognitive Security Institute is dedicated to providing a forum for practitioners and researchers to discuss the fundamental cognitive security challenges of our time. The views expressed by presenters are their own and do not necessarily represent the views of, or endorsement by, the Cognitive Security Institute or any affiliated organizations. Tyler Malloy received their PhD in cognitive science from Rensselaer Polytechnic Institute in Troy, New York. Their thesis project included work applying generative artificial intelligence methods onto reinforcement learning techniques to better predict human decision-making. Since then, they have been a postdoctoral researcher at Carnegie Mellon, working at the Dynamic Decision-Making Lab under the advisement of Professor Gonzalez on projects involving decision-making in cybersecurity contexts, including phishing email identification, security resource allocation, and network analysis. Now, here is Tyler.
All right, great, thanks. Yeah, my name is Tyler Malloy. I am a postdoc in the Dynamic Decision-Making Laboratory at Carnegie Mellon. And today I'll be talking about cognitive modeling of decision-making in cybersecurity. So just a quick overview of what I'll discuss. The first thing I'm going to do is introduce instance-based learning, which is the cognitive model that's used in our lab to try to understand and predict human decision-making in dynamic tasks, such as those in cybersecurity environments. Then I'll go through some background on previous applications that our lab has done in cognitive modeling in cybersecurity. And this includes human-computer interaction as well as individualized phishing training. Most of the focus of what I'll be discussing is this individualized phishing training, as it's also what our current research is in applying generative artificial intelligence with cognitive modeling onto improving how we train people to identify phishing emails in that training program. But firstly, I just want to give a special thanks to the other members of the Dynamic Decision-Making Lab, especially our PI, Professor Cody Gonzalez. We have some great postdocs and PhD students working on a lot of great research here. Yeah, and with that, I can get into an introduction on instance-based learning. IBL is a cognitive model that seeks to model and replicate the cognitive mechanisms that are implicit in learning and decision-making in dynamic environments. So the way that works, firstly, is by modeling human recognition. So we have someone interacting in an environment, and they have memory of previous instances in that environment that are made up by the features of the state that they're in, as well as the action that they performed in those states. And based on the similarity between the current state of an environment and the ones held in memory, we make a prediction of the expected utility of the different actions that are available to someone in that specific state of the environment. So that leads from the cognitive mechanism of recognition to judgment. And then based on those predicted expected utilities, we make some selection of the best action to take, or we choose to explore different options if necessary. And then this model and the agent makes some decision in the environment and executes it, which has an impact on the environment, which can change the state and also result in some utility feedback, which is then fed into memory. So that state of the environment they were in, the action they performed, and the utility that they observed is what makes up the memory of this cognitive model. So firstly, a little bit more detail about recognition. This cognitive mechanism is instantiated with the following equation called the activation equation. And so this value is made up of three components. The first one is a weighted term that has a decay parameter d here in the exponent that differentially weights instances held in memory based on how recent they are. If you're in a very dynamic and changing environment, maybe one where there is an opponent who is changing their strategy as you engage in the environment, then it might be more important to pay attention to very recent instances in memory compared to ones further back in memory. The next term is a weighted noise, which has this sigma parameter, which controls the level of noise that's added to this activation value. And this controls for some randomness in the memory of humans and also in their resulting behavior. And then finally, this third term is a weighted value, which uses this alpha parameter, which sums over a set of functions that are comparing the individual features of a decision-making task. So if I have a task with 5 different features that are determining what good behavior looks like in that environment, then I am presented with a new part of the environment. I'm comparing for all of the instances that I'm holding in memory, how similar this current state of the environment is to all of the instances that I hold in memory. And that allows me to determine how relevant an instance in memory is for determining correct behavior in a new and novel state of the environment. And so with this activation function, we can calculate the probability that an instance in memory will be retrieved and ultimately used in determining the value of a novel state. So this is done with a simple softmax equation, which produces a probability distribution over these activations and also uses this temperature parameter to control how uniform that distribution is. And then with this probability of retrieval, we can estimate the expected utility associated with performing a specific action in a given state by summing over all of these different activations held in memory, as well as their outcomes, using the probability of retrieving that instance in memory. And then when we actually go about selecting the action, that's typically done by choosing the action that is available to us that has the highest expected utility at a given point in time. So there are a lot of different applications for instance-based learning, and here I'm focusing on the ones related to cybersecurity. In cyber defense, we're interested in modeling the human decision-making that goes into how cyber attackers might be designing their attack strategies, and similarly, cyber defenders, how they can best react to these human attackers. And then finally, the behavior of individual users that are impacting things like networks and other cases. There's also the case of phishing detection training, which is the main focus of my talk today, but I'll briefly go over these other ones. And here we're interested in best educating people to identify possible insecurities in phishing emails. And this is a big challenge because the general public oftentimes is not as well versed with the typical issues that might indicate something as being risky. And also, strategy of the attackers who are designing these phishing emails is constantly changing. And so that's why we're interested in using instance-based learning and try to identify how people are learning in phishing detection training. There's also another instance, which you might have read from some of our recent work, of human-AI interaction. So this in the bottom right is the cyborg environment, which is a very simplified version of a network analysis task where a cyber defender is analyzing network traffic and determining whether or not they need to shut services down or if they need to investigate some of these services to see if they might be compromised. And here we're interested in making recommendations to these cyber defenders that can result in the best outcomes for this network analysis environment. So if we take an environment like this network analysis task, one way to model the attack defense behavior in this environment is by using a instance-based learning model of the human attacker's behavior, as well as modeling the end user's behavior, and then using the predictions of their behavior in the future to inform and allow for human defenders to design adaptive and personalized defense strategies that can best protect that network against attack from humans, while also accounting for the desires of users. And then another example is the phishing education email task. So here we assume that someone is writing a phishing email. We can also use instance-based learning to try to understand how they are choosing the features of the phishing email to send out to people. And then a key part here is that we can also model the behavior of the end user that's actually deciding whether or not they want to click a link in an email or reply with some information that could be dangerous. And here this allows us to define an adaptive and personalized strategy for educating the person best in how to identify phishing emails in the future. And so these are just two examples of cybersecurity environments that our lab has worked on. In the top left, you see this phishing training, which is pretty realistic, but not exactly extremely complex compared to something like this network analysis task. There's also that network analysis task, which is called Cyborg. There's even more complex ones called Cybervan, which seek to fully replicate an entire sort of realistic network and a lot of traffic that is involved with that. But we're also interested in very simplistic environments like this box game, which is a signaling task based on Stackelberg security games. And here this allows us to think about how humans interact in defense and attack scenarios and how we can best model the sort of other agent that's interacting with people in these tasks. And so with that, I can get on to talking a little bit more about how we apply cognitive modeling into the domain of cybersecurity. So with this, I can get into a little bit more detail about the Cyborg environment. So here we have a very simple network, which is consisting of just two users in this user subnet. There's two enterprise servers in the enterprise subnet, and then one operational server in this third operational subnet. And this environment, this task, involves an attacking agent who gains access firstly through the user subnet and is trying to work their way through the subsequent layers of this network and eventually reach the operational server where they can deploy an attack and compromise some of the resources on that. And the goal of the human defender is to monitor the network behavior and then find where the attacker is and respond to them by shutting services down or controlling the movement of the attacker. They can also do things like adding honeypots to the network, which can slow the progress of the attacker through the network by confusing them about the true sort of configuration of this network. And here the interaction between humans and computers comes in the form of an AI recommendation system, which gives a recommendation about what action a human can perform in this task. So at every time step of this environment where we're trying to find out where this attacker is and shut them down, there are two actions that can be performed. And the human makes their selection, and then the AI makes a recommendation about what action to perform, and then the human can either approve of that action or change it to a different one if it thinks that there's something better to be done in that environment. And we can compare different strategies for the selection of this AI model and see how well the human and AI team performs this task based on the individual strategy that's controlling that AI agent. And so here is a comparison of three different strategies, and we're graphing the amount of effort that's exerted by the human participant on this left graph here as the 7 episodes of this environment progress. So in the blue, we have a randomly controlled AI agent who is just selecting a random part of the network and then choosing a random action to perform on that network. And this requires the highest amount of effort to perform the task from the human participant, which is obviously not ideal because these people can only look at so much of these networks at a time, and ideally we'd be making that effort as low as possible. And in the green, we have another agent who is supposed to be designed to perform approaching the sort of ideal action that can be performed in a specific environment state. And the way that works is essentially by having a table lookup of what the state of the environment is and what ideal action could be performed there. However, we can see that this heuristic agent, when it's teamed up with a human, doesn't actually optimally reduce the amount of effort used by that human. And that is instead observed by having an AI agent that's controlled with an instance-based learning model. And so here we can see that the amount of effort required by people when they're teamed up with an instance-based learning agent is lower from this sort of somewhat optimal heuristic evaluation. And part of the reason for this is that instance-based learning is trying to reflect the realities of human decision-making in terms of forgetting the far past and making their judgments based on similarities of the current state of the environment with different ones. And so it can be more dynamic than this heuristic approach, which is totally static throughout the entire running of this experiment. And because it's better able to update, we can see that it's initially very close between the IBL and heuristic models, but that the amount of effort that's exerted by the human in this task is decreasing at a faster rate with the IBL model. We can also look at a metric called the efficiency. And so this is taking this human effort value and then dividing it by the amount of reward that's observed. So the efficiency is better when it's higher, and it's essentially saying if I have some amount of effort, it's okay to increase that effort as long as I can observe some increase in reward as well. And here there's an even bigger difference between the IBL model in orange and that heuristic sort of somewhat optimized version of it. Even though they start off very close together at the first episode, there's a big divergence, and by the end the humans that are paired up with instance-based learning agents are much more efficient than ones paired with the heuristic. And then the random has a totally flat line in efficiency because the humans aren't able to behave optimally when they're paired up with an agent that's making random selections. And so the next thing I'll discuss is anti-phishing training. So this is a very interesting area of research in cognitive modeling because it's one of the biggest factors for how human decision-making can impact the security of an organization or other things, or just individual security and privacy. And part of the reason is because the general public oftentimes doesn't have the correct information required to appropriately identify whether something is a phishing email. And so the idea is that we can hope to incorporate things like generative AI and other approaches in cognitive modeling to improve the training that we have for participants. And this is a classic example of a phishing training environment where we have some email that's presented to a human participant, and we ask them whether or not it's a phishing email. We ask them their confidence, as well as what they would choose to do in the case if they were presented with that email. And we can use instance-based learning to model very accurately the decision-making of individuals when they're presented with this task. So here we're comparing the performance of humans at the top set of these whisker plots, and then the instance-based learning model on the bottom. And this is their accuracy. Here it's the mean suspicion score, but it's also true of their accuracy in judging something as being a phishing email when they're presented with both ham emails and phishing emails, and also whether those ham and phishing emails are simulated or if they're from a real-world data set. And so this motivates the use of instance-based learning algorithms in trying to improve this anti-phishing training. And one of the ways that we're going to try to do that is by looking at optimizing the features of the emails that we're showing to participants. And more specifically about how we model and predict the behavior of individuals in this phishing education task is through the equations that define the instance-based learning model. And the features of the email that we use include things like who the sender is, the subject of the email, and its body. This can also sometimes include features of emails that are a little bit more difficult to collect automatically from emails, like whether or not the subject of the email seems suspicious, whether the body of the email includes urgent language or makes an offer to someone for win the Powerball or something like that that we typically see in phishing email examples. And all of these serve as the features of our instance-based learning model that can model and predict human learning as it progresses in this task. And what's really useful about this is that we can use this model of an individual's learning progress and alter the sort of values that we're giving them to try to see if there are any gaps in their learning that we might want to fix through further instruction in phishing education. So if, for instance, one individual is more likely to click on a phishing email if the topic about it is work compared to something random like dogs, then we could hypothetically give them in their training more examples of phishing emails with that type of topic and teach them that this is another case where you have to be wary and this might change other things that you might need to pay attention to in phishing emails. So here, that sort of general idea gets at the idea of personalizing anti-phishing education. And so here we are comparing in the top right different sort of strategies to training an individual participant. On the x-axis, we're showing the proportion of ham and spam emails that are shown to an individual during the training. And then on the y-axis, this is the metric of the type of email that's being sent to them. And so we can try to optimally select the cluster, the strategy of training an individual, and then as their training progresses, maybe they get better at identifying correct and incorrect judgments on one cluster, and so we can switch to another one that might use a different proportion of ham and spam emails or a different type of topic or type of email that's shown to the participant. And then on the bottom right, we are showing a simulation of an instance-based learning model, their progress and learning over time. And we're showing that by trying to optimize the selection of these strategies, we can actually improve the speed of learning of that instance-based model that's simulating how humans are learning in this task. So this motivates trying to personalize anti-phishing education for individuals and really get at the gaps in their knowledge that might be keeping them from performing this task as accurately as possible in the real world. And so that gets to the current research focus, which we have, and I'll be going over a new experiment that we're currently in the process of designing that's going to be run very shortly. And so I'll give some context in generative AI, as well as how that's being applied onto phishing email identification training, and then some preliminary examples of the tasks that we're going to be showing to human participants. So firstly, the main idea of applying generative AI in cognitive science has received a lot of interest of late because of the huge successes in generative AI. And so here I'm showing different ways that we could possibly integrate generative AI into a cognitive model. At the top left, I have something that's called the common model of cognition. And this seeks to represent in a very basic way that can be easily understood the functioning of a cognitive model. And this is really useful because it can allow us to compare different cognitive models in how they instantiate things like working memory, how they have perceptive faculties, and how that ultimately impacts action, as well as how these different cognitive mechanisms are interacting with each other in the cognitive model. And so one idea of how we can categorize and think of the application of generative AI onto cognitive modeling is by considering what areas of this common model of cognition we could either replace or augment with generative AI. And so on the top right, I have a version of this common model of cognition, where the actions that are being selected by the model are being done by a generative AI model. And this is really useful because the GAI models are oftentimes producing extremely complex outputs. They can be things like images, even videos, text, audio, and all these things that have in the past been very difficult for us to think of as being outputted by a cognitive model. And one of the ways that's often done is, as you saw in the case of an email, instead of thinking about the features of this email as all of the information we could possibly consider, we tend to try to simplify that in terms of whether or not the subject is suspicious, just so that the model is able to more accurately learn and reflect the realities of human learning. But what GI allows is for us to incorporate that more complex generation of things like natural language or visual things or audio that have in the past been difficult for cognitive models to incorporate. Another way that we can add generative AI into a cognitive model is through the formation of memories. And here I've included two different types of memory formation that could hypothetically be done using a generative AI model. Firstly, in perceptual memory and also in the generation of long-term memory. And here really the idea is that a big portion of cognitive modeling involves taking something that's being perceived and then forming some representation of that very complex perception that is easy to store, can be held in working memory, and is also easy to make decisions based on. And so obviously in long-term memory, we don't want to be including extremely fine details about our environment, and instead we want to form low-dimensional representations of it, and that's something that can be afforded by generative AI, because if you think about a model that's creating text, it naturally is required to form representations of whatever stimuli space it's working in that are useful for the neural network that is instantiating that generative model. In terms of applications of generative AI to cybersecurity, so this is a list from a recent paper that was essentially detailing all the different applications of GI and cybersecurity that they thought would either be relevant in the near future or they saw as already being very relevant. Two of the big ones that are most related to this work are social engineering and also phishing emails. However, automated hacking through the generation of code automatically by generative AI models is also somewhat related to what I'll be discussing in this phishing email identification task. And then also on the cybersecurity side, none of the ones that were listed in this paper are exactly related to phishing email identification education. The closest one is probably threat intelligence. There's also a lot of different applications of how we can think of generative AI as being useful in cyber defense. And especially coming from a cognitive science perspective, a lot of these, both on the offense and defense side, are involved with human interaction. And so it definitely will be of a big concern in trying to understand, as this landscape of cyber offense and defense is impacted by generative AI, what does that mean for the humans that are interacting with these systems? And so here, this is an example from this paper of a phishing email that is generated by ChatGPT. And oftentimes when you request something like this from GPT, it might end up saying, I can't do that, or I don't want to give an example that could be used for phishing someone. However, with relatively simple prompt engineering, we can actually get it to write these emails that could be used in a phishing campaign, which is definitely concerning from the defense side. And it's something to think about as we consider the future of educating people on how to identify whether something is a phishing email. Similarly concerning is the automated generation of code. So here, this is generating an HTML code that can display a web page, and this could also be used in a phishing email where we can start to automate the incorporation of features of an email that might make it much more realistic looking. Maybe it could be, it looks like it was sent from Amazon or something, and that can be a lot more difficult for people to identify in these phishing email education tasks. And so the goal of the current project that we're working on is to augment that cognitive modeling of attack defense in something like phishing email or even in the network analysis task and try to understand how generative AI impacts it. And so here we're assuming that a GI attacker is going to be producing the email that's shown to a participant in this education task. And we're trying to model their behavior in determining the features of that phishing email that's being sent to an end user. And we're also trying to model the learning and progress in identifying the features of a phishing email that are relevant to an end user so that we can give them adaptive and personalized feedback that achieves the best learning outcomes. And this can be done through a GI defender, which might be just deciding how to best design an email that's shown to the end user, or best give feedback after they make a selection in a specific phishing email instance. And so this is an example of an email that I created that I had GPT create. It is interesting. It includes this. It attempted to include a link to the Amazon logo, which would have been very convincing, but it didn't actually work. However, I do have a data set of a large number of these that are sent from multiple different companies, all generated by GPT. And in some of them, they actually do have working links. So you can automate a lot of this process of designing a very convincing looking email. However, it creates some link to a suspicious looking site instead of a genuine one. And so that is the sort of first half of the current model of our research. We have a foundation model, which is a generative pre-trained transformer, here ChatGPT 4, and that is designing example emails to send to a human participant to make them look as convincing as possible, to educate that person about what generative phishing emails might look like. Once that human makes a judgment of their belief about what the email is, if it's ham or spam, those decisions are fed into a cognitive model, which is designed using instance-based learning. And once we have a model of an individual's behavior with a few examples, we can query that model and ask it, okay, for this individual, what features of an email are most likely to confuse them or get them to incorrectly label something as either being safe or unsafe? And the way that's done is by using a representation of that email that's learned by a large language model and predicting the behavior of the human participant so that we can give them the best learning outcomes in the future. And so in the past, our previous work and others that have been looking at applying instance-based learning have used large language model representations of emails in this phishing identification task. And they've actually found that we can predict with a very high degree of accuracy the behavior of participants in assessing whether an email is safe or dangerous by using the representation of that email formed by a large language model and treating that as the feature of an instance-based learning model. And so this is really great because we don't need to find the individual features of a specific email. We don't need to collect that by asking human experts whether or not a subject is suspicious or if it has an urgent tone. Instead, we can automatically use these large language models to form representations that are useful for predicting the behavior of humans. And just to contrast this with existing approaches to educating the public and professionals about phishing emails, this is an actual screenshot of Carnegie Mellon's recommended course in phishing education. And here we can see a few features that might not be somewhat ideal. It's typically using very plain text in it, so we can think that if someone's getting experience in this task and then they see something like the example I showed previously generated by GPT, it may be difficult for them to identify it as a phishing email. It also uses fake company names, and also there's a very limited number of examples in this training set. And the reason why there's such a limited sample is that the feedback that needs to be designed has to be specific for this example email. If you incorrectly label one of these emails as being safe when it's actually dangerous, then this program will highlight the relevant area of the text that you should have paid more attention to. However, this isn't possible with a large database of emails that are generated by something like GPT. And so that motivates the use of foundation models like GPT in designing the individualized feedback that we present to humans in the tasks like this one, where we have some novel phishing email that may or may not be safe, and we're presenting it to a human. They make their judgment, and we want to give them feedback that they can understand. So the model can output natural language feedback and explain the features of a specific email that are relevant for making a judgment. And this also actually allows for a discussion portion between the human participant and the teacher where they can clarify anything that they thought might be relevant that wasn't mentioned by the model in producing their first output. And again, this is being informed by the cognitive model, which can allow the foundation model to highlight specific areas of an email that might be more relevant for an individual based on that individual's learning progress. And so this GAI-produced feedback can work for both very simple emails like the following one, where this is generated from a predefined set of emails that had in the past been used to educate people about phishing emails. And additionally, it can take into account the learning progress of that human. And so this is what our website looks like that we're going to be running human participants with very shortly. So we can show them some phishing email. Here the participant incorrectly labeled it as not a phishing email, and they said they were very confident about it. And the GAI model uses information from the instance-based learning model, which predicts which features of this email the participant might have been ignoring, and also the contextual information related to the email that was shown to them in crafting its description of what information might be useful for providing feedback to that individual. And also here we can see this very naive user says, oh yeah, I understand all that, but I really wanted to get the Powerball, and the GPT model is very kind. It doesn't call them stupid for saying that. It gives them some feedback of saying, okay, you want to win the Powerball, but it's still dangerous for them to do that. And so we need to understand that. And so this is really great from the point of view of providing feedback automatically in a way that doesn't require us to have this predefined data set. Because if you were to perform one of those learning tasks in the past, like this one, if you were to do it 2 or 3 times, you'd be repeatedly seeing the same examples over and over again, whereas with this approach, we can define new ones on the fly and still give feedback related to it. And this can also work for more complex emails that are actually generated by models that include cognitive modeling. And so here is an example of that earlier Amazon one that I showed you, and the human performs this task. They say, no, it's not a phishing email. However, the feedback presented to them is to describe why this sort of address, the sender, is dangerous, and the link of this button is to a fake website, and so they should be concerned about that. And so this participant says, oh, I thought that this was a phishing email because the logo didn't load properly. However, they're able to use the contextual information about this being an email from Amazon and the logo not actually loading, and the previous learning from this participant, which said maybe they'd be more likely to incorrectly label something as phishing if the logo doesn't load properly, and craft its feedback to send to that participant in a way that's very easy to understand. And again, this conversation period is very important, and it's something that's missing from current approaches of automating the education of people about phishing emails. So it's really interesting to see. This is a brand new study, and it's one that we're going to be running very shortly. And hopefully the idea is that the sort of full training model, which uses emails generated by our combination of GI and cognitive modeling to craft the best examples, as well as providing individualized feedback, is going to produce the best learning outcomes for individuals in identifying whether something is a phishing email or safe. Yeah, that's everything that I have. Thanks so much for inviting me here. I have a lot of time for questions, and here are my references.
Thank you for taking the time to watch this presentation to the Cognitive Security Institute. You may learn more about topics in cognitive security by visiting us at cognitivesecurity.institute.